All right, thank you for joining us for the California Fire Science Seminar Series, and we're going to go ahead and get started. So, hello, my name is Minho Kim, and I'll be your host for today. I'm a member of the student committee who assisted with organizing the California Fire Science Seminar Series. And to introduce myself, I'm a fifth-year PhD candidate in environmental planning at UC Berkeley. I work on fire spread modeling and creating decision support tools for wildfire risk management. I use computational modeling, geospatial data science, and network science for my work. Also, briefly about our seminar series, the California Fire Science Seminar Series is organized and supported by the California Fire Science Consortium, the Fire Research Group at UC Berkeley, and UC Merced. The student committee was also integral to the success of this seminar series, which included 12 students and postdocs from across the nation who helped select speakers and topics for the series. And so, to note, this webinar is being recorded and it will be posted on the California Fire Science Consortium website and YouTube channel. So, following today's presentation, there will be a Q&A session. Please feel free to add any questions you have to the Q&A chat throughout the presentation. So without further ado, today's seminar, Extreme Wildfire Ecology, Lessons Learned for Integrated Fire Management, will be presented by Marc Castellnou. He is a strategic wildfire analyst and incident commander with the Catalan Fire Service in Spain since 1999. He has served as chief of the Bombers Graf Forest Fire Branch since 2001, and he has been the director of the Catalan Prescribed Fire Program since 1999. Since 2016, he has been a senior expert member of the European Civil Protection Mechanism, and from 2011 to 2020, he served as the president of the Pau Costa Foundation. His work has been recognized widely with the IAWF Safety Award in 2015 and the Batefuegos de Oro Award in 2021. He is also a Master Fuego professor at the University of Lleida in Spain. Now, please join me in welcoming Marc Castellnou.
Hi, Minho. Thanks, everybody. So I'll, I'll introduce today how we consider the extreme wildfire ecology, how we are trying to understand extreme wildfires and apply what we understand and the lessons we learn to manage wildfires here in the Mediterranean and Europe. I'll close my camera just to make things steady because we are under a windstorm in Spain today, so internet is not, it can be cranky. So extreme wildfires, we started in 2017 in this Pedra Grande fire that probably you've seen already. It's an extreme wildfire and that just created piracy B in the afternoon and killed 64 people. So that fire surprised us because we didn't expect that late in the day, and especially we didn't expect that downburst. So all the fall of the plume or the landscape. So that changed the whole understanding of fires and the management. So all the politics was to pressure and put more resources in the ground, put more helicopters, more planes, more fighting, and stop fighting in the landscape. But we tried to understand fire behavior and we tried to understand how all those things were working. So from 2016 to 2020, we went through a tipping point worldwide. We start to see those extreme fires everywhere. So before that, extreme fires also happened. But after that 2017 year, we saw a string of extreme events going from the Portugal ones to Chile, Las Máquinas, to Argentina, La Pampa fire, to the British Columbia, the California fires, the Australia fires, and the Mediterranean fires again, and back to Argentina, like the ones we have seen in Patagonia and Argentina the last 2 weeks. So it has been the last 10 years has been busy for the whole fire community. We cannot say it's a new thing. We just can say this thing is speeding up. So all those extreme fires are bringing us as a firefighters are just closing our window of opportunity to fight fire. In this plot, this is just for 2021. In 2021 in Catalonia, if you look at the plot at the x-axis, you can see the fire line intensity in kilowatts per meter. And then distribution, the orange distribution, a distribution of intensities we had in 2021 as the expected intensities. So if we run a simulator and try to using the surface weather, the topography, and the fuel types, we will get an average of 4,000 kilowatts per meter. But the observed one measured by satellites and rate of spread accounts from the firefighting reports were situated at 8,400 kilowatts per meter. And this decoupling between observed and expected, it's important because at 10,000 kilowatts per meter is accepted when you have the limit of the fighting capacity. See, more than 10,000 kilowatts per meter, it's a limit for us firefighters to survive on the fire line. So although we were according to the planning, just having a conditions normal conditions because intensities were not really high. We're in the middle of the window. In reality, the gap is closing. So we are losing the opportunity to manage fire. And for us, that meant we are losing the opportunity for manage fire and to manage forest and apply low intensity fire or work with the fire ecology to manage our landscapes. So we started to look at options to understand better extreme wildfires, and that's where our research is going as a fire service. So of course, pyroconvection it's being blamed for that. So the pyroclouds, the condensation in the plume, like those ones that I selected from your California fires in 2020. So that the creator of the pyrocumulus, the rising that creates a deep indraft, and that's what it's accelerating the fires. But also the downdraft thing, which is once the condensation gets to really high tops, creates ice, and then creates a downdraft of the cold air, expanding the fires dramatically. So it seems that there was no kind of chance to understand that chaotic behavior. And for us, that was pushing all of us to the defensive mode. So we were just trying to fight fires, trying to defend our population, our cities, but it was difficult to apply management of wildfires, lead burn policy, or prescribed burn, and during wildfire, or change a wildfire classification into prescribed fire. So the reason why all that was happening, it has been deeply assigned to the fuel load. So the fuel hypothesis is what we are looking at. So this plot was done by Al Viva, and we worked with him in the Australia fires 2009. And that was showing the Black Saturday fire. There you have the limit of the 10,000 kilowatts per meter. And you can see that during the day, we went over that threshold of 10,000 up to 90,000 kilowatts per meter. But looking at that plot, that we saw is that, okay, when you have extreme conditions, your fire intensity goes over the 10,000. But if we run a simulation of the intensity we expect, depending on the amount of fuel, if 15,000, 20, 30,000, and 15 tons per hectare, 10 tons per hectare, 5 tons per hectare, we can see that below 10 tons per hectare, the intensity was not over the 10,000 kilowatts per meter. So the lesson learned for us was, okay, we can be in the middle of the worst meteorological event, but still, if we manage well, we can overcome those events. So it was a lot of pressure to increase the fuel management. But out of that reasoning of the problem of extreme fires is due to pyroconvection, moist pyroconvection, and full load of fuel drying to climate change is creating those events, we saw problems with the narrative. One problem with the narrative was the onset of the dry pyroconvection. So this is Santa Coloma fire in Catalonia. It's a moist pyroconvection event. It stays in the narrative. But this is Paradise Fire in your California 2019 was not in the narrative, and this is Valparaiso Fire in Chile. Neither in the narrative, it's dry convection, not dry convection. So out of all those problems, the dry convection was not fitting in the narrative. And a lot of the extremes fires we've seen in the world in the recent years are created by pyrocivs, but a lot of them, like the Bolivia, like the Chile, some of the Mediterranean, some in the United States and Canada, become to the dry convection, no pyroclouds. So in that no pyroclouds, we lack that intense indraft, and of course we lack the big downdraft. So we had another problem in the narrative, which is that when you look at global fire and you classify them by the hour of the maximum run, and you expect to see those fires during the day, at noon, or during the afternoon, when the dryness of the fuel is higher and the instability of the atmosphere is higher, then you realize that the extreme fires the last 5 years are shifting to the day to night transition and deep into the night. And that it's not normal because it doesn't use the optimal burning condition during the day. Of course, we can have windy nights, or we can have different effects in the night, but we will not see that global trend. The other thing is that, for example, in Bolivia 2019, we saw one of the biggest fires in the Chaco area. It was almost 1 million hectares and was extreme runs. In this map, you can see the runs by the day done by one of our team members, Mercedes McFisher. But that's a fire in 2019. But then when you look the fire in 2021, which is 2 years later, the fire did even faster runs during a day. And there we didn't have the fuel built up. So not all the energy of those fires was coming from the fuel combustion, and not all the energy of these fires was coming from the moist convection, because those fires, especially, they didn't create moist convection; they were driven by dry convection. So clearly, we were not seeing the whole picture. And if we want to manage this fire and we want to still use the fires to manage our landscape and apply fire ecology, we need to understand what's going on. For that, we set up into a measurement of different fires. So using Chile campaigns and using European campaigns, we measure almost 200 fires and launching sensors inside the plume. We know we can do that with radars, or we can monitor them with satellites, but we need the detail of launching them and measuring the composition of those plumes. So what we found is that the volumetric, the mass flux of the plume was defining the plume, and especially the rising velocity was the key metric. Either we were launching the zone from behind, from the flank, or from the head fire. They had different profiles, but all of them were defined by the rising velocity, that max flux. Of course, we were not expecting to measure the core of the plume. We were expected to measure the cubic meters per second that move on top of the square meter of burning flames. And we compare that with the ambient zones, launching zones on outside and launching zones in inside. And that identifies as that the metric that better explain the change in the plume and the characteristics of plume was the rising velocity. And that rising velocity was being used for us to identify conditions. And we saw that the cumulative rising velocity or the volumetric flux of the whole plume was defining the type of plume. That plume with its small pyrocumulus, you can see the profile here of the rising velocity to the top, and the same fire, but not in a uphill run creating pyrocumulus, but in a downhill flanking, it creates a totally different profile of rising velocity. And if you pile up those data and compute the volume per square meter per second, you can see there are totally different profiles. This fire has the potential to create a pyrocumulus if it's going uphill, but going downhill, it stays manageable, and it can be managed. So if we can understand the mass flux of a plume, we can understand the moments of the fire, and we can understand the stability or the instability of that fire behavior, so we can start to have some clues on how to manage those fire. And that's kind of piling example of 5 different types of plumes. And I want to show you that it is not exactly the speed of the core, but it's the average speed of the volume moving through the plume because as you can see, some of those shallow plumes can have still 5.6 meters per second, and almost 1,000 higher plumes are only 4.8 meters per second. In general, it's true, like those five profiles show, that the faster the higher they go, the faster they rise. It's the upper set of plots, and the lower set of plots are showing the humidity. So up here we see the rising velocity, down here the humidity. So it's clear that the higher and the moister, the faster it goes. And if the faster it goes, it means it can move more air, so it can create bigger indraft. It can change the fire to the extremes. And that variable, not the condensation, was explaining the dry convection and the moist convection extreme events. And that was fitting more with what we were observing. Of course, the higher plumes, they create condensation, and through the latent heat release, they even speed it faster, the rising velocity, so they create more extremes. But it was not an exclusive thing of the moist convection. It was also part of the dry convection thing. So using all this data, we could correlate a correlation between the average velocity and the Ross bias, which is the difference between the observed rate of spread of the fire and the expected rate of spread of the fire. So the expected is the one we can compute using only surface conditions, classical models, and fires burning inside the atmospheric boundary layer. And the observed one is the one the fire accomplished burning with the surface condition plus the coupling. So the Ross bias relation was correlating very well with the adverse velocity, which at the end was correlating with the cape the plume was creating. So basically, the mass flux was the variable we were trying to use. So we went on and we tried to run different simulations of turbulence in large eddy simulations, like those ones you can see here. In the upper part, you can see the turbulence created in the normal day in the atmosphere, and the lower part, you can see the turbulence created by a fire, and how the turbulent layer behind the fire, it's pretty much the same, but ahead of the fire and downwind from the fire, it's a much higher ABL. So if that's changing the ABL, I mean it's changing the height of the injection of the plume, and changing the height of the injection of the plume, it changes the volume it moves. And it change the volume it move, it changes the rate of spread. So basically, we call that fire ABL. Instead of calling that the atmospheric boundary layer, the one we are trying to run the simulations in to understand the physics of fire, the modified ABL by fire ahead of the fire, it's creating different conditions. And when we compare that with 2,000 fires around the world, we saw that basically the Ross bias, which is what you have below in the x-axis, it correlates. The Ross bias is not, doesn't correlate with the height of the fire ABL, but it correlates with the modification of the fire by the fire ABL, with that difference. So the change the plume is creating on the ABL, and it's affecting that change ahead of the fire. It is explaining, it is concentrating all the Ross bias, and of course all the Python clouds can be added in there, but also a lot of dry convection is in there. So mass flux can change the ABL, but that advection of the ABL, it is changing, it is creating conditions that allow the fire to rise the plume faster, or the volume more steady, and that it's what's creating the change on fire spread. And that is not unique of moist convection. It's moist convection, is dry convection. There is a lot of variability on that, and that's a variable that can help us to explain a lot of the difference of those fires, and how those fires transition from dry to moist and moist to dry, how they became big, how they are stable and unstable. So one important thing, as you've seen in the zones, is that when we run the plume models adjusted with the data we get from the radio zones, we can get a sensitivity analysis for a fire according to the size of the flaming zone, how high the plume will go. That's the vertical rising velocity profile we get from models in the upper set of plots, and in the lower set of plots, you can see the amount of mass flux the fire is moving. And as we say, that amount of mass flux the fire is moving correlates with the bias of rate of spread with increased acceleration of the fire. But still, all this is is sensible to the size of the fire, the size of the head fire, not the size of the burn area, the size of the head fire. So basically, when we want to see or we want to try to understand how the extreme fires behave and how we can apply ecology and those principles and those extreme fires. We need to account for the plume injection, but we need to account for the mass flux moving through that plume, and that's a balance between the size of the head fire, the mass flux the fire is moving, and the injection height. And that's an interaction with the free troposphere, the ABL, and the conditions on the surface. So apart from the conditions from the surface and the conditions of the plume, we need to look for the balance between height and volume the plume is moving. So with that, right now we are looking at those fire. And as you can see in this fire, this flank of the fire, this fire is creating a pyrocumulus, but that pyrocumulus is increasing the indraft, but that indraft is allowing that fire instead of the windy day to underburn those old Pinus nigra stands that we want to manage. So during extreme wildfire, we still can produce those effects that we need to manage those events. And now that we know what to look, we can go and we can model that. So we produce a plume top sensitivity to the head flame area size. So based on the area size, we can run the model by different intensities. So every different blue line corresponds to intensity. It's 20, 40, 80, 160 kilowatts per square meter, and we can run that based on the models by hour. It's been adjusted by our measurements, plume measurements, and with that we know which size of the fire creates which injection height and that which amount of volume it moves, and so how much indraft it create and how if that is stable, if that's changing, and on which size of the burn we can allow, so we can start manage those fire to achieve different types of fire behavior, and so to achieve different types of effects. So that's an example of the previous fire. So in this previous in that graphic, you can see that at 3 hectares in size of the head flame, we will get the jump from 3,000 meters almost condensing to create a deep pyroconvection with high condensation, and that's exactly what we saw from 1726 to 1742 to 1752. We went from a Ross by of 0.9, which means fire was behaving as expected, to 1.6 to almost 3 when creating the pyrocumulus. And that was the expected thing. But then the fire went over 3 hectares, so it becomes almost 8,000 meters injection. Ross bias was up to 14, and that was the change from the surface plume in the ABL to the vertical development of the ABL. So that's the kind of things we can predict. And like in this fire right here, as you can see, it's a flat injection height, independent of the size. So that fire is not going to change, and fire is going to be stable. So if the previous fire wasn't stable, this fire is pretty stable. So you can plan in this fire a lot of burning or let it burn. It is not going to become any extreme despite the size of the fire or the evolution of the event. And that allows us to start to see into the fire behavior, to start to see into how our fires behave. So in these fires and these plots, I need to explain that a little bit. What you see here is that by every hour, you can see those gray numbers that tell you the size of the head fire. So 0.5 hectares, 3 hectares, 5 hectares, 10 hectares. And the situation of those numbers every hour in every hour axis tells you the height of the injection plume we expect with the conditions of those days. So as you can see, this fire in the middle, which is Pan de Vilomar in 2022, it's a fire that has the injection height pretty much stable all the day. and at night it's collapsing a little bit. So it's a fire which is the problem. Extreme behavior is not going to be fueled by the atmosphere. If there is any change like this one you saw here, which is that overshooting pyrocumulus, it will come from change in the surface. So if you increase the fire because it's a change in the slope, it's a change in fuel type, the fire can increase the amount of energy and can increase the height. But it's not instability coming from the atmosphere. So it's something that depends on what we do on the fire, it will create the changes. The upper fire, which is in the column Keral, which is that nice pyrocle, as you can see, the injection high it's pretty much stable again through the day, but at night, in the afternoon, in transition, it peaks. I mean, there is a lot of instability coming from the atmosphere. I mean, that fire, the extreme, it's unstable. It will have conditions to create extreme, to move more volume of air, to increase the size, to increase the intensity because there are changes in the atmosphere. So it's a totally different fire. This one up there is a totally different fire than the one in the middle. That one is something we cannot control. It is driven by the atmosphere. The energy comes from there. It will transform dry convection to moist convection. But this one in the middle, it's a fire that's pretty much stable and it can overshoot if the fire in the surface change because it change on fuel or change in surface, but it's not going to it's pretty stable fire if we manage that. So we can align the flanks, we can let it burn. It will not create anything complex. And the fire down there, it's another fire. It's a dry convection fire, the classical fire that collapses through the night. So it's a fire that will not inject higher, will inject less height every time into the night. So the plume it's going down, the INRAF is being reduced, and the burning conditions will be poor at night. So now we have operational tools that translate all the coupling, the complexity of the turbulence of the coupling into basic models that allow you to understand the forces moving the fire to the extreme. It means you cannot quantify them perfectly, but you can understand the moment, so you can, as operational, you can take decisions when to turn a fire into let it burn fire, when to manage the flanking or the backing of the fire to burn more surface and create an open savanna type forest, or when you have to get your people out of there because it's safe, or when you have to put the fire out because after that moment the fire is going to explode or to become extreme. So for us, it is important to make sure we are looking at a fire and the fire is not something that we are lucky when we put it out, or we look at them as let's hurry, we have to put them out as soon as possible because the risk is extreme in the surface, it's hot or it's windy. So we still, with this knowledge, we can start to use the hot days or the windy days or highly extreme days to use the fire, the extreme fires, and manage our landscape, or to understand how they evolve and how they grow. So all these models, it's what we're applying those days also in Patagonia, and we're trying to teach those models to apply them more globally and understand them. So when we look at those fires, and we look at the evolution we've seen from the beginning of the century, in the last 10 years, from the big fires we saw in the first 10 years of this century, on the big fires we see now in those years, and the change on rate of spread. Back 10 years ago, 10 kilometers an hour was almost extreme. Now we can see 25, 26, 30 kilometers an hour, and it's becoming normal every year, and the same the number of hectares. I still remember 2017 when we saw the 8,000 hectares per hour in Las Máquinas fires in Chile, but now it's becoming normal, or like the 14,000 hectare fire we saw in Portugal. So despite that evolution, that it's frightening, there is kind of logic behind that we are starting to understand based on direct measurements and based on the transition from normal fire in the ABL, dry convection top of the ABL, moist convection, but that transition is modulated by the mass flux, which is that velocity of volumetric velocity of the plume, and that allows us to identify the moment of change, the stability of the plume, or the instability of the fire, and the moments we have to leave it out. But those are the lessons learned in terms of extreme wildfires globally and the ones we can apply to build up in our management or to bring our prescribed burning season or management into those fires. So extreme fires are not anymore a limitation. I think we can hope to start using them really soon. Mm, that's the main body of the talk. And now there's questions. I'm more than happy to discuss them. Thanks.
All right, thank you so much, Mark. We will now open it up for questions, and due to time constraints and high attendance, we kindly ask that all questions be submitted through the Q&A chat in Zoom. Um, there's one question from Juan Pablo Galvan Martin. Is, he asked, sorry for not following, but what is the narrative? Can you describe the fuels versus weather narrative again?
Sorry, can you say it again?
Yeah, so they're asking what, because you were talking about the narrative when you were explaining in the beginning. Can you explain a bit about the narrative?
Yeah, the narrative of the extreme wildfire, it is that mainly what is driving the extreme wildfires are big fuel build-ups, but we are saying we can see a lot of extreme wildfires in light fields or areas burned recently, like the one I showed in Bolivia. So we get a fire in 2021 burning over a fire in 2019, and the fire in 2021 one even more extreme than the one in 2019. So that was kind of contradictory about what we call the fuel hypothesis. So the extreme events or extreme fire spread seems to be driven a lot by extreme weather, by a lot by the pyroconvection or the energy the fire can extract from the turbulence in the atmosphere, especially the turbulence on the top of the ABL. That the narrative we had at the beginning was go all for full management, but some of the fires were contradicting that. I mean, still high intensity fires and dry convection fire or moist convection fires, they still need to burn that fuel to get the energy. But some of those fires doesn't need that big amount of fuel. That was the contradiction in the narrative.
All right. Thank you, Mark. And I have a question as well. So the first one is, how can people from different fire backgrounds, so scientists, policymakers, indigenous practitioners, community members, and so on, how can they work together to shape the future of fire ecology?
So the future of fire ecology, it means we need to understand fire and we need to understand our forest. So in the context we are right now, we are all trying to defend our forests, but our forests, they were born in a climate that is not here anymore. So they are stressed. They are not healthy. So either we manage them to make them healthy, or we help them to evolve, to regenerate after a disturbance and adapt to the new climate. And that means understanding and acceptance. And that's something we don't have. We have fear. We don't want to lose what we have. And what I've been explaining or the lessons we are getting is that, well, okay, extreme fires are big and are fast because they have a lot of energy to be released. But they still open the space for the new forest to come in. And I mean, our landscape are not healthy because they are under big thermal stress, and they need to readapt.
Mm, yeah. Thank you, Mark. I have one more question to follow up on that. And I was just wondering, what is one fire-related misconception you find that the public remains to be struggling with, and how can we work to address it collectively?
Well, the main misconception is that fire is bad. Now we've been through a generation changing the concept that okay, high intensity fire is bad, low intensity fire can be good. But still we some of the things we've seen, for example, the recent paper published by Ruth Domanic about the Californian database, looking at database, we found that the prescribed fire, they create homogeneous effects because we modulate the effects to achieve what we're going to achieve in the landscape. So in fire needs to create biodiversity. So we need to understand that low intensity fire is good, but homogeneity is not good. I mean, those extreme fires, they need continuous homogeneous landscape. So the only way you can break the fire intensity is through change on fuel types, change on the energy being released into the plume. So it's not slow intensity fire or high intensity fire, which is good or bad. It is that homogeneous fire behavior that is not good. We need the biodiversity, and high intensity has its role in the biodiversity. Some of the pesca burns we do cannot manage some of the fire of the ecosystems we have. We need extreme conditions to get a head fire creating an indraft to keep the backing fire burning the conditions we need. Because if we burn without that head fire, we don't pull air out of the plot we're burning fast enough, so we scorch the ground. So there is still a lot in extreme fire we need to know, and that's the fear we have to lose, and that's what we need to understand. And that biodiversity, it's a need. We cannot just focus everything on the low intensity.
Mm, thank you. Um, For further questions, um, here's another one. So, um, continuing from what you were explaining, so then what area of fire science or like wildfires should we, uh, well, what areas of fire science and wildfire is not receiving the attention it needs in order for us to be prepared for the future, especially considering what you're talking about?
Well, the coupling with the atmosphere, it's too complicated still. It's belonging to the physics and the simulation, it's really costly. So all that modeling and all that physics need to evolve to make those tools kind of applicable and general use to research. So what we've been showing is a conceptual modeling, but as you know, getting a proper numerical simulation to apply, it's something that is still some years away. So and that's the kind of field that needs a lot more expertise. Let me explain an example. So Dixie Fire, it's California fire. It is from 2020, 21. One of those nights, the Dixie Fire was slowing down in the unmanaged area and was speeding up in the managed area. And that same effect has been seen in some fires in Greece, some fires in Spain, some fires in other parts in Chile as well. The reason why the fire was burning a lot through the managed area, it was a less dense fuel, and the fire could move the amount of air at a constant speed. So the other fuel, which more dense, the fire couldn't move enough air. So he was losing momentum. He was losing injection height. He was calming down. But in the managed area, he was keeping momentum. He was keeping the volumetric movement, and he was keeping the high intensity fire. So those fields, those simulations, that understanding is where we need to focus because is that frontier between the low intent or the management fire we can manage and fire that becomes extreme. That transition up and down is that we need to understand better.
Yeah.
And that means that we need to understand that looking at the feed troposphere, not the surface and the ABL. It's looking the surface and the feed troposphere, which is where the two things that couple in a fire.
Yeah, thank you for the explanation. I mean, I have so many more questions about this that I want to ask you, but we have a list of questions in the Q&A. So this is from Timothy Chavez. Hi, Mark. Is there something we can measure on the ground to indicate the presence or not of potential for a fire to become extreme? Is it lapse rate or wind at different levels, or is it something else?
Is the mass flux. Mass flux, the volume of air moving per square meter of flame. And that's something that is complex, and we need to develop the metric. The metric is clear in the models, but that metric it is not clear as a firefighter. So the balloons offer you the opportunity to measure that. we have to see, of course, I'm sure that radars can do that, but you have to move the radar really close to that plume because you need those lower part of the plumes. So that's a research field we have to develop. So maybe the profiling from satellites can help in the plumes, but we still have to measure. The tool of profiling is still too young to have enough plumes properly. So the old profilings didn't have the resolution enough resolution. Now maybe, but a combination of plumes. And now we are trying with Oklahoma University, we're trying a new tool which is with a drone using a balloon as a beacon because the drone doesn't know how to follow the core of the plume. But if you launch a balloon, the balloon follows the core, and so the drone can follow the balloon. So we are there, but needs more cooperation between fire services.
Very cool. So this is the next question from Jessica McFarland. Great talk, Mark. We know climate change is enhancing extreme fire weather and fuel aridity broadly, but I'm wondering if you can talk more about how climate change is impacting the atmospheric dynamics of these extreme wildfire events.
One thing that is surprising us, it is climate change is driving the fires to the night. And I know there's a lot of research that is saying, okay, longer nights and hotter nights are creating those conditions for the fire to keep through the night. And that's true. But those conditions in the night doesn't mean extreme fire. So why extreme fire is happening in the night? What we've seen in our measurements is that dry convection is losing buoyancy on average 2,000 to 3,000 meters on top of the fire. If you don't reach condensation, that means latent heat release, you don't get the push to keep rising, so you lose the momentum and your plume stays there. So with climate change and hotter days, the average boundary layer is getting higher. So for the fire, it's difficult to create that moist condensation during the day. But because we keep the nights hot and dry, but the ABL is going down at the night. For the fire, it's easier to do that at the night if he has enough energy to be released on the surface, which is it has because the nights are hotter. So that's the main effect that is killing us as a firefighter because when we get extreme fires, we rely on the night. But if we're losing the night, then we got the opportunity, we lost the opportunity. And that's the main change that I've seen in different parts of the world.
Oh wow, right. And that those are all the questions I have here so far. If you have any more questions, you can also reach out to the California Fire Science Consortium, or you can try and reach out to Mark as well. And we're going to just kind of wrap up everything for today's session. And I want to thank all of you for joining us. Again, a special thanks to Mark for his enlightening presentation. And it's really interesting and fascinating how he's working on all these cutting edge things um, to understand extreme wildfires and the ecology. Our next session is scheduled for February 6th at 11 a.m., where we will be discussing operational outage, ignition, and wildfire risk modeling at PG&E with Scott Strenfel. Again, before we sign off, please keep an eye out for the webinar evaluation that will be sent out soon. Thank you once again, and I look forward to seeing you all in our future sessions. Have a great day. Thank you, everyone.